So that said, today,
oh, we lost Anne. I think the connection might be an issue.
Oh, she must have dropped. Well, I think at this point, we were just about to hand it off to you, Professor Ban, to introduce Jingxing. So, so I guess we will, I can take that.
And coming back,
So
yeah.
why don't you go ahead?
Okay. And you want to continue, or you want me to?
Yeah. So the way we kind of envisioned it is,
Okay.
is that Anne or I would introduce the sort of the series, and then each student's advisor would introduce the student.
Okay, sure. I make it very quick because of the time.
well, by the way, I clicked, you know, it said the meeting is recorded, and I wanted to click it off, and I clicked on close the meeting.
Okay.
Sorry.
No worries.
No worries.
So Jingxing has been working with us since 2016. He's a fifth-year PhD student working on a few things, but most noticeably the transportation big data project funded by Federal Highway and WashDOT, and also we collaborate with Professor Cynthia Chen's team, been helping developing methods and frameworks to evaluate big data and how to use that to compute traffic measures and performances. Also, keeping in mind the bias and other issues of big data. From there, that also motivated him to work on, human mobility patterns and the sources of those, like the demand, right? So without demand, we don't need to work to travel. So that's sort of his kind of motivation, using how the data can help that regard. This is, I see why the participation is not huge, because this is a very classical topic. It's not like the fancy and the emerging topics like big data or AI that people talk about every day. But this is a very, key, not so, one of the challenging problems in transportation networks. And Jingxing offered some new insights and some new methods. And I think the result is very solid. We've been preparing a paper to submit to Transportation Science and a few other papers to Part B and other places. So I think with that, I stop here and let Jingxing to start his presentation.
Yeah, thank you. Thank you, Jeff, for your introduction. Good morning, everyone. My name is Jingxing. Today, I'm going to present some of my research work on OD estimation, especially to introduce the insignificance-based origin destination demand estimation of the large-scale network. And here is my outline of the presentation. First is the background. So we know human mobility is changing dramatically in intensity and complexity, and different cities own very different mobility patterns. For example, in the figure 1, we saw that Paris and Los Angeles shows very different trip generation hotspots. And the third figure which is from one of our project, showing that showing the trip generation hotspot of the Greater Seattle area. So it can be seen that different cities own very different trip generation pattern. So a good understanding of the large-scale travel demands is very essential to many stakeholders. For example, the transit agency, DOT, local planning agency, city, and mobility service provider. Another motivation of this study is from the increasing availability of the data. So traditionally, the travel demand are directly calculated from sample survey, for example, the household travel survey, roadside survey, but this kind of method is usually costly in time and money. And when the product became available, they are very easily becoming outdated. So later on, the traffic link counts and prior OD information were the main source to infer OD demand. But such method require wide deployment of surveillance devices. And nowadays, with the large-scale mobility sensing data, it has become one of the most promising supplementary data source for OD estimation. And because of the low-cost, large geographic coverage and the longitudinal features of such data, it has provided many new feature or promising directions for OD estimation. The third one is from the insignificant property of the OD demand matrix. So such insignificant property was recognized but not properly treated for OD estimation. For example, the OD demand matrix, if you look at the left figure, it shows that the element Dij means the demand from origin I to destination J. But if we look at the OD demand matrix for the large scale network or for the large scale area, we may notice that most of such OD pair only on very small demands. For example, if you look at the top right figure, it shows the insignificant OD, shows an example of an insignificant OD matrix. But previously, such insignificant property was recognized as the sparse OD matrix, where most of such insignificant demand are treated as zero. But that may not be true according to the OD product from local planning agency. So based on this, we try to understand the insignificance property of the large scale matrix and try to propose some new method, especially to focus on such insignificant property. Traditionally, the OD demand estimation was kind of a combination of the prior OD demand as well as some newly acquired field data. So in this, and they are often divided into two categories. One is static OD estimation, where the OD and link flow do not vary with time. Another is dynamic OD estimation. In our study, we only focus on the static OD estimation. Traditionally, those OD estimation methods share such very similar formulation. That is so-called general least square formulation, where we try to minimize the general least square between the OD estimate and the prior value, as well as the link flow estimate with the observed value. And the estimate of the OD demand and the link flow has to follow some certain traffic assignment constraints. So having been recognized such sparsity property of the large scale problem, there are only a handful of literature using the sparsity-based OD estimation method. So this kind of method is inspired by a so-called compressed sensing technique, where we try to minimize the L1 norm of X subject to some AX equal to B, where the number of variables is much greater than the number of constraints. So by using the L1 norm, we can somehow recover the variable X. So based on the compressed sensing idea, there are a few literature comparing with the compressed sensing with the traditional OD estimation model that is widely recognized by the equation 2. So basically, the main difference between this model and with the traditional general least square model is that they usually introduce such L1 norm of the estimated D times some weighting parameter lambda, and for each model or for each new network, we have to turn such hyperparameter. And here are some comparison between the existing OD estimation method based on the sparsity assumption. So the main issue for such OD estimation method is, first, the sparsity assumption is too restrictive. In reality, those insignificant OD pair do not necessarily have the zero demand. And in addition, they often need to turn the hyperparameters. So we propose the insignificant OD estimation framework. First, we have to define the insignificant OD demand. For any given OD pair, if an OD pair only has very small demand, for example, if the demand of the certain OD pair is less or equal to some user specified threshold epsilon 0, then we call it as an insignificant OD pair. And the definition 2 tells us if an OD demand matrix have so many such insignificant OD pairs. For example, if the condition 1 is satisfied, which means the number of insignificant OD pairs takes dominance in the total number of the OD pairs. And the second one is the total demand of such insignificant OD pairs only takes a small portion of the total demand of the entire network. So based on the definition of the insignificant OD pair, as well as the definition of the insignificant OD matrix, we develop such IOD framework. And here we made a very important assumption. That is to say, given the same threshold parameters and the insignificant OD pair set, the prior OD demand, which is from local planning agency, also share the same insignificant property with the true OD demand. So that is to say, the prior OD demand from local planning agency is very representative of the true OD demand. Then we formulated the general IOD formulation. In the objective function part, we use the L1 norm of the deviation between the estimate and the prior information, or the estimate and the observed link flow. And here the function psi here describes some traffic assignment conditions as well. And we have to note that the insignificance is less restrictive than the sparsity assumption. So we only assume that those demands are very small, but not necessarily be zero. But on the other side, such insignificant assumption is more general than the sparsity assumption, because if the D0, which is the prior OD equal to 0, the IOD model can also capture the OD sparsity property. Here, based on the IOD framework, we developed two models. One is the fixed mapping IOD model. Another is the bi-level IOD model. So for the fixed mapping IOD model, the estimate of the OD demand and the estimate of the link flow follow such fixed mapping relationship described by the mapping matrix Q hat. And then we have to define a set of K, that is the OD demand that satisfies the insignificant property for the given insignificant OD pair set W. Here is the definition of the K. So if we denote D hat, V hat as the optimal solution for the fixed mapping IoT model, then the OD insignificant consistency question we consider here is if the prior OD demand D0 belong to K, will the estimated OD demand D hat also belong to K? Then we have such theorem 1 for the fixed mapping IoD model. That is to say, if either of the following two conditions is satisfied, the OD insignificant consistency held. The R1 is the L1 distance from D0 to the boundary of K. R2 is the L1 distance between from the D0, V0 to S, and R2 hat is the L1 norm between the two terms. So the theorem 1 basically give us sufficient condition for such OD insignificant consistency. If either R2 less or equal to R1 or R2 hat less or equal to R1, we can certainly say that the estimated OD demand will share the same insignificance property with the prior OD demand. So for better understanding, we illustrate the theorem 1 in this figure. Basically, it said that if R2 is less or equal to R1, then the optimal solution of the fixed mapping IoD model D hat will be also within the insignificant OD pair set K. So here is a remark for such theorem. If one certain condition satisfied, the estimated OD demand will share the same insignificance property with the prior OD demand D0. And under assumption 1, because we assume that the prior OD demand is very representative of the true demand. So under assumption 1, the D hat will own the same insignificance with the true OD demand. And it only requires the prior OD demand D0 is representative of D bar, not necessarily close to D bar. Next, we discuss the solution property of the fixed mapping IoD model. We basically consider if the prior OD demand D0 itself is sparse, whether our estimated OD demand will be also sparse. So we have the theorem solution property, which is a theorem 2. That is to say, if you look at this definition, the W0 means the estimated OD demand which equal to 0, and PZN represents the index of the OD pair which has demand larger than prior value, equal to prior value, or less or equal to prior value. And since this is in the fixed mapping case, we can directly plug in the constraints for this definition. This is to say whether the corresponding link flow is equal to 0 or greater than the observed link flow, equal or less than the observed link flow. So the theorem 2 here shows that the uni of the two sets, which is either equal to 0 or equal to prior value, and the dimension of this set plus the dimension of this set is greater than the total the dimension of the OD pair. So so we further, based on the theorem 2, we further have some corollary, which is to say the number of estimated OD demand equal to 0 is lower bounded by some value. So this value is the number of 0 demand in the prior OD demand, as defined in equation 8. So here is a remark 2 from the theorem 2. That is to say, if the prior OD demand D0 is sparse, the estimated OD demand D hat will be also sparse. And IOD models can capture, can keep the sparsity property of the D0 if the D0 has such sparsity property. Also, as the fixed mapping model can be readily converted into a linear program, we can use some method for linear program to check the solution uniqueness. And next, I will briefly go through the bilevel IOD model part. So the bilevel IOD model part is different from the fixed mapping model because in the constraint part, we introduce the user equilibrium assignment, which is written as equation 11 and 12. So basically, in the fixed mapping model, the traffic assignment method, traffic assignment condition was described by some fixed mapping rules, but in the bilevel IOD model, it has to follow the user equilibrium assignment. And similarly, we derive the solution, the OD insignificant consistency theorem, as well as the solution property theorem, follow the similar logic. And here, we have to note that the theorem 2 and theorem 4 exist no matter condition for the OD insignificant consistency are satisfied or not. And next, I will briefly go to show some numerical results based on the 2 model introduced before. Here, we employ 2 network example. One is a very smaller one with only 5 nodes. Another, we use the downtown Seattle network as an example. So we can see that especially for the real network, the number of OD pair for the large network is much greater than the number of link. So once we only have the link flow data, how to estimate the OD pair OD demand will become an issue for such large-scale OD estimation problem. And in the numerical examples for the large network, we assume that the true OD demand, or we call it the benchmark or ground truth OD demand, can be identified by the local planning agency, for example, the PSRC. Although we know that such demand is an estimate as well, may not be true, but it can be very representative. Then for the small network, we consider the OD insignificant consistency as well as the solution property. So by introducing different errors into the prior OD as well as the observed link flow, we give such 6 trails like this. So basically, we can say that if the condition in the OD insignificant consistency can hold, then when the prior OD belong to certain insignificant OD set, the estimated OD will be also belonging to the set of K. And in addition, it further indicates that the theorem 1, which is the OD insignificant consistency, as well as the theorem 3 for the bilevel case, are only the sufficient condition for such insignificant consistency. And also, we show some result for the IOD solution property for the small network, which is the sum of the two value should be greater or equal to the the dimension of the OD pair set. No matter for the fixed mapping case or bilevel case, we have proved that, proved the statement of the theorem 2 and theorem 4. And we further show an example of the result of the IOD models by solving the small network. So this column shows the true OD demand, and this column shows the prior OD demand, D0. And from the IOD model, no matter for the fixed mapping IOD model or bilevel IOD model, we can see that the estimate OD demand will be mostly equal to the prior demand or equal to 0, like this. And also we note that by using such IOD framework, the root mean square error of the OD estimate will be still less than the prior demand, which means that the OD estimate from the IOD model has been get improved compared with the prior OD demand. Similarly, we show some results for the large network example. Here we use the root mean square error and the accuracy alpha score to measure our model. So for the accuracy and the alpha score, if the value are very close to 1, it means that the OD insignificant consistency will be better held, and the root mean square error, the smaller the better. So by introducing adding the error into the model, we note that no matter for the fixed mapping model and bilevel model, most of the OD estimate will keep the same insignificant property with the prior OD demand. And also, we show some result for the solution property, which shows that for the fixed mapping model, the sum of the previous 2 value is greater than the third value. But for the bilevel case, since this is an solution this is not an optimal solution, but a solution very close to the optimum value, we cannot directly prove that the theorem 4, but it has shown the training that the value for the dimension of the union of the 2 sets are very close to the OD pair set, the dimension of the OD pair set. In addition, we also show some advantages of IOD model over existing OD estimation method. Use the generalist square model as an example. We show that the IOD model have high capability in keeping OD insignificant consistency, and usually they are more robust to outliers in the prior data or observed data. And computationally, such IOD model is less demanding than the generalist square model, especially under the bilevel case. And in addition, they do not require any proper weighting, and they didn't require the hyperparameter tooling either. Here, I show some results by changing different weighting for the generalist square model. It can be seen that
I would recommend you can skip those detailed results and see if people have questions.
Okay. Yeah, so let me briefly talk about the practical insight of this study. So in the past, most of the existing models require the prior OD matrix be close as possible to the true demand, which is very difficult to achieve or check in practice. But under the IOD framework, they only require the prior OD matrix can capture the relative magnitude of the OD demand of the network. So it is very important to explore the representativeness of the prior OD demand, or of the OD prior OD demand matrix. And also, since the IOD model is more general than the sparsity-based OD estimation model, then once the prior OD demand has such sparsity property, the IOD model can also capture the sparsity of the large-scale OD demand OD matrix. So that is how we can say that the IOD framework shows lots of advantages with than the existing OD estimation method. So that's it. I have to thanks our coworker for this study. And here are some selected reference I used in this presentation. Yes, thanks. Any questions?
Okay, thanks, Jingxing. We have a relatively small audience, of course. So any questions for Jingxing's topic?
So just to get started, a general question, because I'm not the right person to look at the technical aspect that I'm sure are very good. But so like when you publish your results, what kind of journals do you publish in, and what kind of places are you trying to apply your novel sort of approach to the modeling?
So currently we are preparing the paper to translation science. So can you say again for your second question?
So the Journal of Science, what journal?
Translation science.
Translation science. Okay. Well, the other part of the journal of the question was, are you talking with like PSRC or other people who do modeling? Are you talking with them and trying to introduce your novel approach?
Yeah. So we had several discussions since 2019. So we have visit PSRC and to introduce our idea of such insignificance property idea for the large scale network, and they agree that this is a very novel idea to model such ODE estimate because as I introduced before, for the large scale network or for the large scale area, no one can know the ground truth of the travel demand, but we can somehow know that the OD demand estimated by the PSRC are very representative. Then based on this assumption, we derive the model that if the prior OD demand can be very representative, then our estimated OD demand will also capture the similar magnitude of the demand.
So the data were provided by PSRC, the initial data. But right. I think Anne has a very good point, is that we haven't talked to them for a while because of COVID. Maybe this is the time to restart the conversation because you have made some progress. We can sort of update that and show the results and see if we can further work on something.
Yeah, that's a good suggestion.
I have two questions for you if you're done asking questions, Anne.
Yes.
So, and they're kind of unrelated, so I'll just go one at a time. For the first question, so you improved your model by including some of the link data that you got. So are there any other sources of data that you think could also be used to help improve this model that may or may not even exist at this point, you know, and just sort of thinking, you know, kind of in the direction of, especially if it's something that doesn't exist, you know, how could we go about collecting that?
Mm-hmm. So that's a good point. Actually, this direction is what I am doing right now. So we are going to, hopefully we can include some mobile sensing data, for example, the GPS data. Of course, not the raw data, but we may pre-process such data and to generate some process data. For example, if we can somehow collect the travel time data from the mobile sensing, for example, the vehicle GPS data, we can somehow incorporate such travel time data into the model, especially for the bi-level model, because you know, under the user equilibrium conditions, the travel cost or the travel time can be easily incorporated into the model. And in addition, we can use such turning proportion data. For example, when given a road intersection, how the vehicle chose their direction at the intersection, go straight or turn left or turn right. So given such data, we can also somehow incorporate such data into the model. Yeah, that is what I will do next step for my dissertation.
Oh, that sounds really cool.
Yeah.
My second question is, and I might be wrong on this, so do correct me if I'm saying something that's incorrect, but I recall that one of the reasons that MPOs use the sparse matrix as opposed to the insignificant matrix is an issue of computational power. It's a lot easier to compute the matrix if more of the values are 0 as opposed to being very small integers.
Mm-hmm.
So how does changing computational power and the growing of computational power and the changing computational methods that we have that have come about quite recently, how has that affected just simply being able to reduce the value that the value at which point the matrix the values for the matrix need to be changed to 0 just from a computational efficiency standpoint?
So I can answer partial of your question. So if I understand correctly, so of course, if we employ this the sparse assumption, definitely this restore sparse matrix will be much easier, or will reduce the memory to will compare with restore a non-sparse OD matrix. That is right. Yeah, but from our standing point for the IOD model is to say, okay, the IOD model will be computationally less demanding than the traditional generalist square, but the generalist square didn't assume the sparsity property either. So our model will be less computationally demanding than that one. And on the other side, the sparsity assumption itself also has some issues. So these issues, we observe this issue from the MPO matrix. So we noticed that from the PSRC product of the King County OD matrix, even there are many insignificant OD demand, they are not necessarily be zero. So I'm not sure. I'm not sure whether you observe you can see other OD products from the other area. So, but from our observation, the sparsity assumption may not be true in reality.
Let me add just 1 or 2 points. So I think Jingxing answered most of it, but there's a first, the model he put together, the so-called LD model, is a more general case. It includes the sparsity as sparse matrix as one special example. Secondly, the model, the model he put together, and in the end, it's also a kind of like a sparsity. It's just a sparsity between the difference of the two, your matrix, your estimate, and the prior. So if you look at the difference, you're still looking for the sparsity of that difference. So it's the same kind of idea to explore the sparsity, but just a slightly different of which you explore. Yeah.
Gotcha.
Okay. I guess
Let's see, there are question from the 2 other people from the audience. Or they probably know each other very well.
Yeah.
Well, still, it's a good idea to ask questions formally, if you have some.
Any questions, Phelan or Yizhan? They probably listened to a few times in the past.
I see. Well, the other thing, though, is to remind Jingxing and that the presentation was recorded, and so you should be able to sort of email your friends and other people who might be interested and use that as a way of introducing your work.
That's good.
Yeah, thank you.
So also my last comment, I mean, if you don't have questions, is, well, I think it's hard for students at this stage, but you do want to customize your slides based on the audience, right? So this is largely still from your general exam to the committee who are more expert in the field, versus to a larger and more public audience. You need to kind of reduce the technical aspect of your slides and be more like the layman type of language to show the significance of your work. Honestly, many of the slides, people don't really understand or don't really care. I mean, you need to sort of balance that to show the significance of your work, but also the significance in practical things, how this help the region or the agencies. If you don't customize, then it wouldn't work very well. That's just, I think it's challenge. I understand, recall my time as a PhD student, like that 20-something years ago. Well, and maybe a bit longer than that, but it's a good learning process. You have to learn that. Think about Jingxing, by the way, will join Facebook, after he graduated. But even that, I mean, you have to, when you do, I'm assuming you intern there. I'm assuming you do experimentation almost every day to your co-workers, to your managers. You have to think about your audience. Who are the audience, and what's the message that you want to convey from your presentation, right? And customize that. You cannot just use one set of slides and present to all different group of people. That wouldn't work well. So that's one of the soft skills we hope you learn when you go out from UW. Not only the technical stuff, which seems to be good. To me, I think that's very solid. But without these soft skills, you cannot really sell your work well. This is my last comment.
Yeah, thank you.
And there are, by the way, if you have a hard time gaining these soft skills, there are people who can help you. Who sort of translate your work, for more general audience. And it could be from, your own sort of classmates, people who are better than you are, if you're not very good at that. And there's nothing wrong with not being very good at, communicating with a larger audience, but you just recognize that you have that, it's not so much a limitation, but you just cannot do that. So you get other people to help you do it.
Yeah, thank you, Anne.
All right. Well, I think we did it, and it's very good. Thank you very much. And then the next, so wary of the next seminar or webinar, I should say. And we have 2 more this quarter.
Okay.
All right.
Sounds good. Yeah. Thank you, Anne.
Thank you very much.
Everyone.
Thank you.
Bye-bye.